Next, I'd like to describe some other forms, some other types of research designs that are commonly used in psychology. First is the quasi-experimental design. So everything we've just described up until now is kind of the nature of a true experiment. And in medical research in particular, we can't do true experiments because we are not able to do random assignment. For example, if you are testing a drug to cure cancer. I or let me give it, yeah, that example works. If you're testing a drug to cure cancer, you cannot randomly assign some people to have cancer and other people to not have cancer to see how it works with people who do or do not have cancer. That just doesn't work. It wouldn't be ethical for you to say, all right, I need you to have, I need to give you cancer, or I need to not, that kind of scenario. You have these pre-existing groups, people who do have cancer, people who don't have cancer, and you cannot manipulate them otherwise. You cannot randomly assign them. And so in those situations, we do what's called a quasi-experimental design, where the fact that where you make sure to control for all the other variables except for the fact that there are pre-existing groups, and you try to match them up on as many other factors as much as possible. It's really common in psychological and medical research. Two other types of designs: a longitudinal design. So that is a design where you follow the same group of individuals over time. So let's say it's very common in psychological research for us to evaluate the effectiveness of psychotherapy in a longitudinal design, where you'll have 50 people who undergo psychotherapy, and you measure them before they start psychotherapy, you measure them after they've completed psychotherapy, and you might measure them 6 months to a year after they've finished their psychotherapy sessions, to see if the gains that they've made in psychotherapy still hold in a longitudinal, a long time after they've finished. An alternative to a longitudinal design is a cross-sectional design. Longitudinal designs are difficult because you have to make sure the same people come back to participate in your study, and you can get a lot of attrition, a lot of people leaving your study. So instead, some people opt for a cross-sectional design where you compare multiple segments of the population. You take people at different time points, and instead of measuring the same individuals over and over again, you measure different individuals at each time point, so that you can still kind of see the progression of things in your study without needing to follow the same people over and over again. Much research, including my own dissertation research, follows a cross-sectional design. The next type of research design, everything that we've described so far is from experimental research. Next is correlational research. So sometimes it's it's good, or you're able to have two very well-defined groups of individuals. You can, people to adopt a high power pose and a low power pose. It doesn't matter what their pre-existing differences are, and it's very easy to split people in half or into multiple groups. Sometimes, particularly in psychological and medical research, it's better just to evaluate people along a spectrum. So to not say low power posing to high power posing, but just to evaluate everything in between. And in that scenario, you might use a correlational design, where you're looking at the relationship between two or more variables. Anytime you hear the word correlation, think of the word relationship. So when we say that two variables are correlated, we mean that they have a significant relationship, that one variable changes alongside the other variable. For example, height and weight, right? There's a relationship between height and weight. The taller a person gets, generally speaking, the heavier they are. That's generally true. It's not a perfectly straight line, but that's generally the case, as well as, for the most part, the number of hours of sleep that you get per night, as that decreases, the more tired you get. So as hours of sleep goes down, tiredness goes up. Those have a relationship as well. And then something else like hours of sleep and shoe size. We wouldn't expect to see a correlation between those things. The scatter plot just looks, just like the word, kind of scattered. And so the stronger the correlation, the closer the data points are to forming a straight line. Here's another more detailed examples of some correlations. So oftentimes in correlation research, we use a correlation coefficient, something like Pearson's R or Spearman's rho, to provide a numerical representation of the relationship between two variables. And so a correlation coefficient tells us both about the strength and the direction of the relationship. Right, so correlation coefficients range from 0 to 1, as well as 0 to -1. So the magnitude, just ignoring the positive and the negative, the magnitude 0 to 1 tells us about how strong the relationship is. So a correlation that's close to 0, or I should say a correlation of 0 means that there's no relationship. A correlation of 1 means that there's a perfect relationship, that these things follow each other perfectly. And so a correlation coefficient close to 0 means that the relationship is weak, whereas a correlation coefficient closer to 1 means that the correlation is strong. It's getting stronger. And then when you add positive and negative, that indicates the direction of the relationship. So for example, a correlation coefficient of -1 would indicate that there is a perfect negative correlation, or a perfect, oftentimes we use the word inverse and substitute that for negative, a perfect inverse correlation. So for example, we had an example of a negative correlation or an inverse correlation would be hours of sleep and tiredness. They go in opposite directions, so they have an inverse relationship. As hours of sleep goes down, tiredness goes up. Um, and then conversely, when you look at height and weight, those have a highly positive correlation. They both, as one increases, the other also increases. Now, a very, very important point in correlational research. If you forget everything else that I say, please leave with this point. Correlation does not equal causation. You may have heard it in other classes. Hopefully, you've heard it before. I just want to re-emphasize it here. It is so crucial to understand that. Sometimes we see a relationship between two variables, and we're tempted to think, oh, because these two variables have a strong relationship, that means one causes the other. Correlation coefficients do not allow us to know, or do not allow us to make causal inferences. That's something you can get from an experiment, where you have random assignment and where all the factors are controlled except for the independent variable that is the only difference between the two groups. That's a place where you can make causal inferences, but not so with correlation. So, for example, it's often said that there's a strong correlation between sugar use, or some people might say ice cream sales, and violent crime. That as ice cream sales increase, violent crime also increases. And that can easily be explained by a third variable, right? Uh, Ice cream sales are higher in the summer months, as well as people tend to be more outside, and violent crime tends to be more common in the summer months. For someone to say or that ice cream sales cause violent crime, that would be totally false. Correlation does not equal causation. Another reason for that is we don't know if it goes the other way. Maybe it could be that committing more violent crimes helps increase ice cream sales. A correlation and a correlation coefficient do not allow us to make causal statements. They only allow us to say that there is a relationship between two variables. Here's another example. There's a great website called Spurious Correlations that I've posted on Canvas that has all these kinds of different examples of things that shouldn't go together, but for whatever reason happen to go together and happen to have a strong relationship. For example, the yearly divorce rate in Maine has a really, really strong correlation with the per capita consumption of margarine, also in the state of Maine. They follow each other almost perfectly on a yearly basis, but that relationship does not allow us to say that getting divorced makes you consume more margarine, or if you eat too much margarine, you're more likely to get divorced. A correlation coefficient does not allow us to make that kind of inference. It only tells us that these two things follow a similar pattern.